Hello, everyone. My name is Meng Zhang. I'm an assistant professor with the ZJE UIUC Institute, Zhejiang University. Today, I will be presenting our symmetrics performance paper entitled Age-Dependent Differential Privacy. So this is a joint work with Professor Erwin Wei and Professor Randall Barry with Northwestern University. Also, a joint work with Professor Jiang Wei Huang with the Chinese University of Hong Kong, Shenzhen. So this work is first motivated by the fact that information usually has the greatest value when it is fresh, and also motivated by the explosive growth in real-time kind of applications and time-sensitive kind of system. So one of the most important examples of real-time applications will be, the autonomous driving as illustrated in this figure. So the individual vehicles, their operations relies on their, real-time information regarding their neighboring vehicles, so that we can see that the timeliness or the freshness of this kind of information, such as location and speed, is the key to the succeed of safe and efficient autonomous driving systems. As a result, age of information as a metric has been proposed, which satisfies which is actually a simple and quantitative metric to measure the information freshness. On the other side of the house, individuals and users, they may also have the concerns regarding the data privacy leakage. Okay, so the privacy kind of information may be carried by the information that we just mentioned before, so that the privacy sensitive information can be exposed to the adversaries and maybe even misused by them. So these adversaries may include, for instance, the hackers and even the companies that may like to make profits from our personal data. Okay, so more than almost 80% of the individuals have expressed their privacy concern regarding their data privacy. Okay, and this is mainly because of the recent frequently happen incidents regarding the data misuse and privacy leakage, such as the Facebook privacy breach incidents. Okay, so as a key technology, differential privacy can actually provide rigorous mathematical definitions of privacy, and it actually enables easy implementations of privacy preserving techniques that actually are tunable noise injection techniques. Okay, and these kind of techniques are provided with the rigorous privacy guarantees by the differential privacy. So the following are two examples of the noise injection. Or for instance, for the Apple's popular emoji example, we can directly add the noise, inject the noise to the original data set, so that they can confuse the adversaries, so that to protect the privacy of individual users. Okay, so another possibility is that we can inject the noise to the analysis results as well, and one of the applications of it will be the federated learning. Okay, so in practice, we also have many types of differential privacy enabled noise injection techniques that are adopted by major companies like Apple, Google, and Microsoft. Okay, so these work mainly consider the nexus of information freshness and information privacy. Okay, motivated by the fact that the real-time applications may frequently generate this kind of privacy-sensitive personal data, so that it may severely compromise user privacy. Okay, so these may include, for instance, the real-time electricity usage readings and the real-time GPS location data. Okay, so this is actually a challenging problem to consider because we have this intricate impacts of the temporal correlations of the underlying data process and the information freshness on privacy. So the key questions we would like to answer in this talk is how should one characterize the impacts of information freshness and temporal correlation on privacy, and design the privacy preserving mechanisms for real-time application. Okay, so here is a brief literature review. In terms of the age of information, extensive studies have been working on analysis, optimizations, and scheduling algorithm design. But this line of work has not considered the privacy, issue. So in terms of the literature related to differential privacy, researchers have been working on designing variants of differential privacy so that it can be applied to different types of scenarios. So one of the interesting design is called the pufferfish, which is an interesting Bayesian differential privacy framework, and it has also was also be extended to some other kinds of applications where we can also study the influence of data correlations or privacy as well. Another related line of work consider the privacy analysis of dynamic databases. And by dynamic databases, we actually have growing databases, and we will need to release the data, the analysis results multiple times. And because we are doing that, we may end up with more privacy leakage in this case. And in this kind of applications, one way to characterize the privacy is to consider composition, okay? Composition of multiple privacy preserving mechanisms in this case. Also, closely related work to this study consider the temporal correlations for dynamic databases, but however, only for some specific and simple scenarios. Okay, so in general, the impacts of temporal correlation and information freshness on privacy will still not be, well understood in the literature. Okay. All right. So here is our considered system model. So we consider a set of multiple users and a discrete time model. So each of the individual users has some privacy sensitive data, and these are characterized by some time variant databases. And the underlying mathematical model will be some stochastic process, essentially a sequence of some random variables. And at this moment, at this point, the only assumption we make is that the process is stationary. Okay, so the process may not even be Markovian, which is actually a common assumption in the literature. Here, we would like to use the XT to denote the aggregate data of all users at some certain point. And we assume that they actually share the same static state space across all the time. Okay, in terms of the modeling of privacy, we assume that each of the users only aims to protect the privacy of its data at the current, corresponding to the current moment at time t. Okay, that basically means that the users may be less sensitive to the privacy leakage in the past, of its historical data in this case. For instance, if a user is using local-based services, users may only care about protecting its current location, although there might be correlations between the location in before and its current location. Okay, so this is also referred to as the event level privacy protection. So here is the standard notion of differential privacy. So we say that the mechanism N is epsilon C differentially private if the following inequality holds. So basically it means that if we change the two databases, if we only change the data of one particular user, one arbitrary user, then the output, the change of the output is going to be small enough. Okay, so that's the key idea behind this notion. And if we have a smaller epsilon C. So where C here characterize denotes the the classical notion of differential privacy. So if we have a smaller epsilon C, that basically means that we have a more restrictive inequality here, so that it implies a higher degree of privacy protection. Okay, and very common way for us to design mechanisms that satisfy differential privacy is to consider the Laplace mechanism. So basically, for any function f, we can always add some Laplace random noise at the output, so that to make sure the mechanism satisfy differential privacy. And we can expect that if we would like to achieve a higher degree of privacy, we actually are required to inject more noises, which means that the variance of the noise is going to be reversely proportional to epsilon C in this case. Okay, so here we would like to consider the age-dependent generalization, our proposed age-dependent generalization of differential privacy. So we call that a mechanism M is age-dependent differentially private if the following inequality holds. As we can see in this definition, age-dependent DP actually depends on two parameters, epsilon and T in this case. And here we are using the conditional probabilities to characterize this bound. So one of the interpretation is as follows. So one adversary received can observe the outcome of the mechanism when the mechanism used the input data at time t, but the adversary is trying to infer about the information about the database at time t. Okay, so we can see that in this case, it's actually measuring the privacy leakage when we're using the data at time t at time 0, and publish the outcome so that so that the adversaries can observe at time t in this case. So that we can see that the age of the privacy sensitive information in this case is exactly t. Okay, and in this scenario, the randomness of the mechanisms come from both the mechanism itself and the underlying stochastic process of data. Okay, so in order for us to characterize the impacts of the temporal correlation and the information freshness, we would like to consider the following metric, which is called the total variation distance. This is a metric to measure the difference between two probability measures. So let's say we have mu and pi. In this case, its total variation distance is captured by the maximum value of the difference between these two probability measures. Okay, as we can see in this figure, where we plot two probability density functions, the maximum difference is exactly this area. So this is actually 1/2 of the total shaded area in this case. Okay, so the most specific metric we would like to consider is the maximum total variation distance. So the probability measures, the probability distributions we are interested in is actually the t-step transition probability of each user's reverse process. And by reverse process, we are referring to the case where the adversary is observing the previous data and is trying to infer about the current situation. Okay, so we have this conditional definition of this conditional probability, so that, and we are actually taking the maximum values across all the users and across all the states. Okay, we are ready to present our main result, which characterize how the temporal correlations, the age, and the original noise level of injection, the level of noise injection on the privacy leakage. Okay, so we say that So if a mechanism N is epsilon C differentially private, then this mechanism is also going to satisfy our proposed age-dependent differential privacy, where this epsilon T satisfies this equation. So one of the immediate observation is that we are characterizing the privacy guarantee based on the maximum total variation distance we just mentioned, and also epsilon C. So recall that epsilon C actually can characterize the level of noise injected to the system. And also as a result, this delta T is the only key statistic features we need in order for us to characterize such a bound. And also there are many data process actually may satisfy some of the nice convergence results, such as the periodic and recurrent Markov chains, where this maximum total variation actually converges to 0 at some geometric speed. Okay. So our proposed method also, showcased methodologies of combining noise injection and aging, as illustrated in this figure, where we can age the input data a little bit, and then inject the noise to the output data, analysis results. Okay, so due to the time limit, I'm going to briefly introduce our numerical results. So here we compared our proposed schemes by combining these two methods together against the classical benchmark that only inject the noise. Okay, and we can see that if we target it at an arbitrarily small privacy leakage, the performance gain can be unbounded in this case. So here I would like to conclude. We actually consider the age-dependent generalization of differential privacy, where we started to analyze the impact of data stillness on data privacy guarantees. And we actually, our characterizations actually motivated a framework which provides a new directions to provide data privacy based on stale data, in addition to noise injection. And our performance gain can be unbounded, as illustrated in our analytical and numerical results. Okay, so we actually only present the first half of our paper, and actually for the second half, we consider the more practical and general scenario, where we consider these multi-query mechanisms that we actually frequently release the outcomes multiple times. We can expect that there are going to be some interactions because of their correlations between the outcome release. And we also consider analysis and to solve the optimization problems based on some composition result. Okay, so for future work, we are interested in considering the user level privacy protection, and the queuing theory related analysis, and also more adaptive composition results to achieve a better performance bound. So this concludes my talk. Thank you so much.